All right, guys, in this video, me and my group mates are going to go over the basics of magnetic fields and how we can analyze them using equations as well as methods like the right-hand rule. And at the end, we'll give an example or a few examples of how magnetic fields can be applied in the real world uh, in technologies and whatnot. Okay, so to start off, just to give some context, so magnetic fields are the result of individual moving charges, point charges that each have their own tiny magnetic forces on them. And when we have lots and lots of these tiny individual charges moving together along a wire, for example, or like through a current, we can see far larger and more significant magnetic fields being created than if the charges were just by themselves. So everything, all these charges have magnetic fields, but when we group them up in, again, for example, a wire, we can really see like a very significant magnetic field, and we can predict their behavior very well based on how they move through the wire. Uh, so to start out, let's just keep it simple and analyze the direction of magnetic fields only, along with the components of magnetic force and velocity. So if we have these three quantities and at least two of their directions are known, we can use vector cross product properties to solve for the direction of the third, the unknown quantity. So as you see on the screen here, if you're not familiar with what a vector cross product is, all you really need to know for the sake of this topic is that if you have two vectors lying on a plane together, so for example, we see vector D and vector C here on the same plane with some angle alpha between them, the cross product of D and C is going to be perpendicular to the plane that they're laying on. So as you can see here, this vector represents the cross product of these two, and it's sticking out perpendicularly out of this plane. So kind of a neat little way we can package this to problem solve in physics is the right-hand rule. So as you can see in this diagram here, so there's many different ways you can do this, but the way that me and my group mates decided was the easiest and easiest to remember is the one you see here, where you would point your thumb in the direction of the velocity vector, you would point your fingers in the direction of the magnetic field, and then your palm would be pointing in the direction of the magnetic force. So the way I like to remember this is that if you were wearing like rings on your fingers, which are magnetic, if they're metal, you would point those toward the magnetic field. And then the way the force points is if you were to slap something, like forcefully, for example, you would point your palm in the direction of the thing you're trying to slap. And that only leaves you with one other way the velocity can point, which is the direction of your thumb. So using that, we can, again, if we know two of these, we can solve for the third one. So for example, if we know the direction of the magnetic force and we know the direction of the magnetic field, we can figure out which way the current is flowing or the charge is going. All right, so this is what like a typical right-hand rule problem might look like. It might, just to go over like the anatomy of this, it might give you a bunch of these like X's like this. And these actually denote the direction that the magnetic field is pointing in. So for example here, we see that the magnetic field is pointing into the page, denoted by X's, and if it's pointing out of the page, as you can see here, that'll be denoted by dots. And the way I like to remember this is that if you were to like shoot an arrow into the page, you would see like the tail of it, like the feathers and whatnot. And if you were to shoot an arrow in the direction coming out of the page, like toward you, you would see the little dot of the like sharp part of the arrow, the tip. So yeah, let's go back to the problem. So if you were to solve this, for example, if we were trying to find, again, here we have the direction of the current flowing along the wire, and we have the direction of the magnetic field, like I just described. So if we were trying to find the direction of the force, the third quantity, we would, and everyone that's watching, you can follow along because it helps to practice this. So you would point your thumb in the direction of the current. So your thumb should be pointing right, because again, we're interested in this little bottom segment here. Your thumb should be pointing to the right, and then your fingertips should be pointing into the page. And that would leave your palm facing up. So that tells us that the direction of the force is parallel to the screen or the page and going upward. So yeah. And then going beyond just directions here, so we can see that if we want to solve for the actual like numeric quantities themselves instead of just their directions, we have this equation, and this is basically just another representation of a cross product. So we have the two vector quantities here, and then we have the angle between them, as I went over at the beginning. So you're going to multiply those, and then this q is just going to be the size of the charge. So kind of like how mass exists in F equals ma. Q is kind of like the analog for mass in this case. So yeah, that'll give you force due to magnetism, or magnetic force. And then if we go beyond that, so now that we have like an understanding of magnetic fields and what they are, it's worth knowing that you can actually create a magnetic field by sending an electric current through a wire, as we just talked about. So like every time you run a current or run charge through something, you're creating a magnetic field. And there's actually another right-hand rule for this. So as you can see here in this diagram on the right, if we run current through this wire going in this direction, we're going to generate a magnetic field that goes circularly around the wire in this counterclockwise fashion. And the right-hand rule for this, we'll go over on the next slide, but just to touch on that real quick. And then another tidbit, we have Ampere's law, which we have over here with this integral in it. And Ampere's law just states that for any closed loop path, so if we were to take this wire and turn it into like a part of a circuit where there's a closed loop, for any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability, this times the electric current enclosed in the loop. So what I mean by length elements is that if you take the integral of, say, like a closed loop, length elements is kind of referring to like if this was part of a loop, if we were to slice this up into infinitely small little pieces, and then analyze each slice of that, we could then use that to make predictions about how the entire length would behave, and that's kind of how the integral works here. So we're kind of cutting this up into a bunch of tiny pieces to see how it behaves continuously across the entire closed loop. All right. And then going further, so this is just another diagram for the right-hand rule we mentioned. So if the current is flowing upward through this rod or through this wire, your thumb would be pointing upward, and then your phalanges should curl around the rod. And since they're curling in this counterclockwise direction, we know that the magnetic field is circulating around the rod in a counterclockwise fashion. Okay. Some real-world applications of all this, of magnetic fields, and what we just discussed with pumping electric currents through wires to generate magnetic fields and whatnot. So we have solenoids, which are basically just a more complicated version of what we just talked about, where you can pump a current through a wire to create a magnetic field. So if you pump a current through a coil like this, a coiled piece of wire, it creates this interesting situation where you have kind of like poles at each end of these loops. So like you might have like, similar to how like magnets have north and south ends, one of the ends of these coils would be a north end and a south end. And then this can be used to create even more interesting technology like electric motors. So electric motors actually do this same thing. So like this picture right here is actually a very simple electric motor. And I highly recommend you do this at home if you have never done this or never seen this. But basically how motors work in at their most like simple form is, so this wiring here has some insulation on it. And I don't know if you can see, if you look really closely, you can see like half of it is shaved off on one side, but the other side, it's not. So basically the current will only flow when this half of the wire is touching the metal, okay, the top half. So basically how these work is this battery will pump an electric current through this loop, right? This like system right here. And when we're pumping the current through, this coil will try to align itself with the magnetic field, with the poles. So it'll actually flip to where this ring is like laying flat with the table. And then when it's flipped, this insulated part of the wire will touch these like supports here, and then there will no longer be current flowing, and thus there will no longer be an electric field being, or there will no longer be a magnetic field being induced. So So that will mean that instead of just stopping once this is aligned with the field, it'll actually keep falling because we've cut off the power. All right, so it'll keep falling due to momentum, and then it'll touch the circuit will be complete again because this will rotate, and then it'll just keep repeating that. So it'll try to align itself, and then it'll fall, and then it will try to align itself again. And this in motion just looks like it's spinning really fast, and it's really fun. Again, I encourage you to try it. But yeah, this is how motors work by inducing magnetic field within like a tightly wrapped coil like this, and like kind of like the more coils you have right here, the faster this will spin because you're inducing a stronger field. But yeah, that about wraps up what we wanted to talk about today with magnetic fields. I hope you guys learned something and can kind of see how this stuff exists in the real world and how people apply it using technology and whatnot. But yeah, thanks for watching, guys.